So hello to all my young friends who are studying in intermediate and they are watching this video. Welcome to the lectures of GTK Academy. In our previous videos, we had covered friction. Today we are going to cover another important and interesting topic, and the name of the topic is uniform circular motion. My dear friends, since I was traveling abroad, I was not able to post videos for quite some time. However, since I'm back, I'll be posting videos on a regular basis and will try to complete mechanics as quickly as possible so that you can take the benefit of these videos for your final exams, which are quite near. Calculus is already complete, mechanics is complete, so you can take the benefit of these videos for your exams, and the remaining topics are also going to be uploaded in due course of time. So without wasting much time, let us start our today's topic, which is uniform circular motion. Now you all must be familiar with circular motion, but what is this word uniform doing here? A question that will come to your mind. So before understanding uniform circular motion, let us briefly discuss what is a circular motion. When an object moves in a circular path, we call it a circular motion. And the peculiarity here is that motion is in a plane. Let me clarify that with some examples. If you tie an object to a string and move it in a circle, which most of you must have done, like this. So if you join all the points in the trajectory of stone, a plane can pass through all those points. You can see in this shaded area. So I think now it will be clear that how the motion is in a plane. Other example is rotation of automobile wheel, which all of you must have seen. Here each and every particle of the wheel moves in a circle. This is again another example of circular motion. Or even you would have read in your books earlier that electrons revolve around the nucleus in circular orbits. This is nucleus, these are electrons. So they also move around the nucleus in circular orbits. Anyway, their motion is not so simple, it's a complex motion, but that is not our topic here. Now circular motion can be divided into two parts: uniform circular motion and non-uniform circular motion. In case of uniform circular motion, particle moves in a circular path, but the speed of the particle is constant. In case of non-uniform circular motion, particle moves in a circular path, but speed is variable. Now let us understand both of them one by one. So let's start with uniform circular motion, which is our topic today. Now in case of uniform circular motion, velocity changes continuously. Now we just made a statement that speed is constant, and here we are telling that velocity changes continuously. So what does it mean? See, speed is a scalar, whereas velocity is a vector. Now scalar has only magnitude, whereas vector has magnitude plus direction. So in this case, magnitude is constant. So for velocity, magnitude will be constant, but direction is going to change continuously. So this changes, the change in velocity is due to change in direction. Let me again clarify it a bit more. For example, this is any particle or any body moving with a speed of 5 meter per second in this particular direction. After some time, its direction changes, but speed remains same. Again, the same thing, direction changes, speed is same. Again, the direction changes, speed is same. So speed in all these cases is 5 meter per second, but if the velocity in this case is v1 and this case is v2, this case is say v3, this case is v4, because velocities is different in all these cases. So v1 mod is equal to v2 mod, magnitude is same, is equal to v3 mod is equal to v4 mod, and that is equal to 5 meter per second. And I hope this is absolutely clear now. So let's move forward. Now you can see from this figure that if a body is performing a circular motion in this circle and it has any position which is represented by this radius vector, and the velocity at this position is say v1, another position v2, v3, v4. In all these positions, only the direction of the velocity changes, its magnitude remains constant. What do we mean by that? That mod v1 is equal to mod v2 is equal to mod v3 is equal to mod v4 is equal to any value, say v, something like that. Now another peculiarity here, you can see that velocity vector is always perpendicular to the radius vector. This is your velocity vector and this is the radius vector, and we all know the angle between the radius and the tangent, because velocity is in tangential direction. You can take any point, even if you take a point here, you will see the velocity is in the direction of the tangent at this point. So this angle is 90 degree. So velocity vector is always perpendicular to the radius vector. Now the important thing to note here is that velocity is changing, because if the change is in magnitude or it is in the direction or both, in all these cases velocity is going to change. And whenever there is a change in velocity, that means there is an acceleration. So due to change in velocity, which is direction here, there is an acceleration. But here the acceleration is a bit different. See, whatever we had read in our previous chapters, or I have also discussed in my previous videos, we used to have motion in a straight line, and there used to be some force in the direction of velocity which increases, and it is called acceleration. If it is in reverse direction, then it decreases the velocity. It was called retardation. But here the acceleration is not like that. Here it's a bit different. And what are the peculiarities of acceleration in this case for uniform circular motion? The magnitude of that acceleration is constant. This is first thing to be noted. And the other thing is direction continuously changes. The direction of acceleration is also continuously changing. Since the direction of velocity is changing, so direction of acceleration is also changes. These two things should be noted about acceleration in case of uniform circular motion. And a very important thing to note here is that at every point acceleration is directed towards center. Say if we take this point, the acceleration at this point, the instantaneous acceleration will be directed towards center. This is a very important thing. Now In case of non-uniform circular motion, velocity changes continuously, but here the change is in direction as well as magnitude. Both are changing. Magnitude as well as direction. So what do we mean by that? For example, take the previous case. In our previous case, if it is a uniform circular motion, mod of V1, V2, V3 and V4 will be equal. But in this case, they can be different. Say if mod of V1 is 5 meter per second and mod of V2 is 7.2 meter per second, can be any value. We are just taking arbitrary value. V3 is say 9.8, V4 is 11.6 meter per second. Any value. These are just to explain you. So here also we have acceleration because there is a change in velocity, but change is in direction and magnitude both. So here the acceleration is variable and is also not directed towards center. So till now we discussed that in case of uniform circular motion, there is an acceleration whose magnitude is constant and it is always directed towards center. And in case of non-uniform circular motion, we have an acceleration whose magnitude is not constant, it is variable, and also it is not directed towards center. Now before we proceed further on this topic, let us discuss few basic definitions which we are going to use extensively in this chapter. Angular displacement. Now what is angular displacement? The angle swept by radius vector in a given time duration. Suppose a body is performing circular motion and its position is P1 and its radius vector is R. After some time, its position becomes P2. So in this time, in this period from P1 to P2, it has rotated by an angle delta theta, or we can say the radius vector has swept an angle delta theta. Now delta theta is called angular displacement. Now you all must have studied in your junior classes a very important theorem of geometry, arc upon radius is equal to angle in radian. This you all must have read. Now here, if delta is the length of the arc, so arc here is P1, P2, that is delta S upon radius R is equal to delta theta in radian. So delta S is equal to R delta theta. Arc is equal to radius into angle in radian. Please remember this result because we are going to use it in the next slide and I think you must be knowing it. Now angular velocity, the rate of angular displacement undergone by a particle performing uniform circular motion, it is denoted by omega. Angular velocity, that means angular displacement upon time taken, that is called angular velocity. Take the same case. In this case, if the particle moves from P1 to P2. Then average angular velocity will be equal to delta theta upon delta t if delta t is the time taken. You must be familiar with this average and instantaneous. I have discussed this thing in my previous videos. Now there is another term which is instantaneous angular velocity at any point. So that is equal to delta theta upon delta t limit delta t tending to 0. This is equal to d theta upon dt, and this is called omega. So we know that what we have seen in our previous slide, delta s is equal to r delta theta divided by delta t, and take the limits. Now this one, delta s upon delta t limit delta t tending to 0, this is v. Linear velocity and instantaneous, and this is your angular velocity. That means we get a relation v is equal to r omega, and many of you must have heard about this. You must be knowing it, that v is equal to r omega. But here there is one thing. R is a vector, radius vector, and omega is also a vector. That means two vectors are being multiplied. Now if two vectors are multiplied, there can be two cases. Either the product is a scalar, then it is called a dot product, or it can be a vector. If the product is a vector, then it is called a cross product. Now here the product is v, which is also a vector. That means this is a cross product of r and omega. Now you all must be knowing that in case of cross product, r cross omega and omega cross r, they are different things. They are not equal. So we have to see whether it is r cross omega or omega cross r. Here in vectorial form, if we write, then we write v is equal to omega cross r. Please note it. See, normally most of the people will be remembering this relation as v is equal to r omega. But the order of r and omega here, since it's a scalar, you can write r omega omega r. But if you write in vectorial form, you have to write it omega cross r. Please note this. So linear velocity is a cross product of angular velocity and radius vector. Now the question comes, we know the direction of radius vector and we also know the direction of linear velocities. Say at p1, the linear velocity will be in this direction b. So what is the direction of this omega? That we want to know. And I think many of you must not be knowing about the direction of omega. So let's talk about the direction of angular velocity, that is omega. Suppose this is a disk and it is rotating about its axis, which is shown in dotted line, and this is the direction of rotation. If this is the direction of rotation, then angular velocity direction is shown by this blue arrow. And if the direction of rotation is opposite, say in this case, the direction of omega is this. Now you must be thinking how to find out the direction of omega. What is the method? The method is use right hand thumb rule. It says that if we curl fingers of our right hand in the direction of rotation, say this is the direction of rotation here. Now if we curl the fingers of our right hand like this, you can see like this, and that too in the direction of rotation, and it should be right hand, not left hand, then the direction of thumb represents the angular velocity like this. You can see that the fingers are curled in this direction. You can see this is the direction of rotation, right? So this is the direction of rotation. We have curled our fingers. So our thumb, direction of our thumb represents the angular velocity. Similarly, in second case, you have curled the fingers in this direction. So your thumb direction represents omega. I hope you have understood this. Now we were telling that linear velocity is the cross product of radius vector and angular velocity, that v is equal to omega cross r. Now we have told you how to find the direction of omega. Now we need to find the direction of v using omega and r. Now v is equal to omega cross r. I hope that you know how to find the direction of cross product. I have discussed this in my video scalars and vectors, that is the first video, but still we'll just quickly have a recap of that. Suppose this is a vector and this is b vector, and theta is the angle between a and b, then a cross b, which is a vector, that is equal to mod a, we represent by a, into mod b, into sine theta, sine of the angle between them, and into n cap. Now n cap is the unit vector in the perpendicular to the plane formed by a and b. Now this is the plane formed by a and b. So n cap is perpendicular to this plane. Now n cap direction can be this one. This is also perpendicular. It can be downward also, like this. Now which direction we have to take? This we have discussed. Again I am discussing. Now since it is a cross b, then what we'll do, we'll use right hand screw rule. We'll keep a screw in such a manner, you can see in the figure, that its axis, this is its axis, that is perpendicular to plane formed by a and b. Now it is a cross b, so we will go from a to b like this. Now if we rotate this screw in this direction shown by this curved arrow, screw is going to move in the direction shown by red arrow. This is the direction of A cross B. However, B cross A is, you have to start from B to A like this. In that case, screw will move in this direction. So the direction of B cross A is reverse of A cross B. I hope you have understood this. Now, coming to our topic, this is the disk and it is rotating about its dot axis shown by dotted line in this direction. Now, if we take any point here, so the linear velocity, if I ask you what is the linear velocity of this point shown in red color, you will easily say that it will be tangential. This will be the velocity. But let us prove by or show it by this cross product. Now, the radius vector of this point is r here. The direction of omega, what we discussed just now using that fingers, curling the fingers in the direction of rotation of our right hand, omega will be, direction will be upwards like this. Now, just extend the direction of r like this, and this is the plane formed by omega and r. Now keep a screw whose axis is perpendicular to this plane. Now this is a 3D figure. You have to just make some imagination. Now it is omega cross r. So if you start from omega and go to r like this, so if you rotate this screw in this direction shown by this curved arrow, it is going to move in the direction shown by a red line. That means this is the direction of V. So V is equal to cross product of omega and r, which will be omega mod of omega. I just write omega into r into sine of angle between them. Now the angle between omega and r is 90 degree. Sine 90 degree into n cap. That is the unit vector in the direction of this velocity. So it is equal to, now sine 90 is 1. So omega into r into n cap. This is in vector form. But if you just take the magnitude, v is equal to r omega. That is why we write it like this. I hope you have understood this. Now centripetal acceleration. Till now we have discussed that when we have a uniform circular motion, we have an acceleration which is always pointing towards center. That acceleration is called centripetal acceleration. Actually, centripetal acceleration means with acceleration which is directed towards center, or center seeking. Suppose any body is performing a circular motion in a circle of radius r, and its position is P1 here with a velocity v1, and after some time the position changes to P2 and the velocity is v2 there. Now v1 and v2 are equal in magnitude. The radius vector from P1 to P2 covers delta theta, and P1 P2 length, that is length of the r, is delta s. Now what we told you initially, that This acceleration, which is directed towards center, it has constant magnitude and it is directed towards center. That I am going to show you how it is. Now, if we extend the direction of V1 and V2 like this, what is the angle between V1 and V2? Can you guess? Just pause the video and guess. I think some of you must have guessed it correctly. See, this angle is 90 and this is 90. So this is a quadrilateral. Now, sum of all angles of a quadrilateral is 360. That means now 90 plus 90, 180. You remove it, then you are left with theta and this angle. Say it is alpha. Now theta plus alpha will be 180. And again alpha plus, if this angle is phi, alpha plus phi will also be 180. That means phi is equal to delta theta. I hope you have understood. Very simple geometry. This is delta theta. Now, since we are finding acceleration, what is acceleration? Acceleration is change in velocity upon time. Now, if we want to find the acceleration from P1 to P2, which will be average acceleration, then what we have to do? We have to subtract V1 from V2. So, now let us draw V1 and V2. This is V1 and V2. So, if you use vectorial methods, V2 minus V1 is this, V2 minus V1, and angle between V1 and V2 we already said that is it. It is delta theta. Now, here delta theta is quite small, but still it has some value. But if delta theta is extremely small, very, very small, then if you see this triangle and this sector, they both will be, we can consider them as triangles. ABC is already a triangle, but OP1, P2 is a sector where P1, P2 is not a straight line, it's a curved line. But if delta theta is very small, then P1 and P2 can be considered as a straight line. Then I can write triangles A, B, C and O, P1, P2. I have written both of them as triangles, right? Since delta theta is very, 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 very extremely small. Now you see, this angle is delta theta. Here also delta theta. This side is V1, this is V2, but magnitude is same. That means AB is equal to AC. And here OP1 is R, OP2 is also R. So that means these triangles are similar. Now, if the triangles are similar, this triangle as well as this sector, which is also we are considering it as a triangle when delta theta is very small. Now, for similar triangles, their sides are in the same ratio. That means BC and the corresponding side is P1, P2. That will be equal to AB upon OP1. Now, BC is delta V and P1, P2 is delta S. AB and AC are V. We can V1 is equal to V2 is equal to V. Say magnitude is constant for velocity upon OP1 is R. That means delta V is equal to V upon R into delta S. Divide by delta T. Divide by delta T. Now, since delta theta is extremely small tending to 0, That means delta t also tends to 0, taking the limits on both sides. Now, this becomes our instantaneous acceleration A, and this becomes our instantaneous linear velocity V. So, we got a relation here that A is equal to V square. We can write it V like that. V square upon R, and V is equal to R omega, omega square, R square upon R. So, A acceleration is equal to V square upon R, which is equal to omega square R. This is the magnitude of acceleration, centripetal acceleration, that is directed towards center, and you can see it has a constant value. So A is your centripetal acceleration. Now I have shown you how the magnitude of acceleration is constant. Now let us talk about the direction of centripetal acceleration. Take the same figure. Now if you want to find the direction of acceleration will be in the direction of change in velocity, that is V2 minus V1, that is the change in velocity, which is delta V, right? So just subtract V1 from V2 and see, this is minus V1, so this is your delta V. However, here we can see the delta V direction is different, it is not towards center. So what is the problem? The problem is we have taken average acceleration from P1 to P2. Delta theta has some value. We have to take acceleration when delta theta is tending to 0. That is instantaneous acceleration, because acceleration is changing every moment. Its direction is changing. So what we have to do? We have to gradually reduce delta theta and bring P1 and P2 closer. And if we do that, see, here I have drawn this sector initiated, reduce delta theta. Now P1, P2, although they have not been shown here, they will come closer. Now this is V2 and this is V1. Now V2 minus V1, delta V. Now delta V, it has now rotated a bit towards center. Again reduce it. The rotation towards center is even more. Again reduce it even more. And if you bring V1, P1 and P2 very close, so that V1 and V2 nearly coincide, which is difficult to show in figure. I have tried to show you. Then V2 minus V1, the delta V is pointing towards center. So that is how the acceleration is always directed towards center. So we can see that acceleration, which is delta V upon delta t, limit delta t tending to 0, that is instantaneous acceleration, is directed towards center, and its value of course is V square upon R, which is also is equal to omega square R, that we have already proved. Hope you have understood. Now in case of non-uniform circular motion, when a particle performs non-uniform circular motion, then it has centripetal acceleration as well as tangential acceleration. Centripetal acceleration is required if it is moving in a circle. Tangential acceleration has to be there because since velocity is changing in magnitude also, that means there is an acceleration in the direction of tangent, because velocity is in the direction of tangent. you see, if any body is performing circular motion, anywhere the velocity is in the direction of tangent v. So you have to have one component of acceleration in tangential direction, and one has to be towards center because it is performing circular motion. So like this is the acceleration towards center, radial acceleration we can say, right? And this is the tangential acceleration, radial acceleration along the radius and tangential acceleration